Okay, so we're still working on our electric motor. Let me summarize. Excuse me. I'm going to summarize in pictures because I like pictures. And so far, what we have is a block diagram that looks like this. Here's our input voltage. Our input voltage, it gets summed with, this is a minus, this is a Ke theta S, and that's theta of the motor. Now I can write this next bit of it in a number of different ways, but I will choose to write it this way. 1 over Rm, there's a lot of just different algebraic manipulation. 1 over tau S plus 1. I'll call that tau 1 again. That's tau S plus 1. And when I do that, that gets me the current. Now, I'm going to multiply this times the motor torque constant and the gear ratio R2 over R1. So this gives me the output torque. And even though in some of the last stuff I did not include this D in here, and oftentimes I will also just neglect that D. Most of the time I'm not worried about what happens on the output. If I grab a hold of the end of my motor, what I'm looking at is how does the electricity that I put into the motor make it move. We'll talk more about this, but this is the net force that's coming to the motor. So the net force, I'm going to write that a different way. That's going to be 1 over B equivalent times 1 over tau 2 S plus 1. So there's 2 blocks here. Notice there's a whole bunch of different ways that I could write this. Sometimes I like to write it this way. Sometimes I like to write it this way. 1 over J equivalent S plus B equivalent prime. I could do it that way, right? If you go back and look, we already did it that way once, and then I kind of changed it into these other variables, so sometimes I do it this way. And when I do that, this is omega out. So I've almost got a block diagram here, but I kind of need to connect this omega out. You know, I don't have anything going in here. So this is what? This is omega of the motor. Well, this is omega out, and what I need to do with omega out, if I want to make it go into the omega of the motor, then what I need to do is I need to make this be R2 over R1. So R2 over R1 converts omega out into omega of the motor. And then I also need to multiply by Ke. Okay, so here, boom. Block diagram all complete. I could go in here and do this in Simulink. Also in Simulink, I don't have to reduce these this way. I can make each individual part as I'd like to. However, you know, I'd make each individual part with the tiny loops inside of it. I might choose to make this tiny loops inside and then put this one right next to it and compare, so using Simulink, so that I know that those are the same thing. Oh yeah, okay, those are the same thing. I didn't make any math errors when I reduced that loop. But look here, oh my goodness, here is another loop. So the first thing I'm going to do with this loop is I'm going to say, you know what, I already did this. This is 1. If tau is really, really, really small, it looks like 1 over something really small plus 1, it's about 1. So I can just leave that one completely the heck out of there. And now I'm going to teach you one more fundamental of block diagram algebra. So what I'd like to do is I'd like to move this summing junction. I'd like to move this summing junction on this side of the block. So I don't want to sum it here. I'd like to sum it here. So if I look, what happens is if I move that, both of those things have to get multiplied by Rm. And if I move the summing junction here, it is not getting multiplied by Rm anymore. And so I kind of need to add Rm. So if I move the summing junction, I'm going to go see if I can find a different color. If I move the summing junction here, I also need to multiply by Rm. And moreover, I don't want it there. Like, this is just one, so it doesn't make any difference. But I'd like all of it to go in here. I'd like all of it to go in there. And if I let all of it go in here, so now I'm going to move my summing junction here. So you'll see I here have to multiply by Km R2 over R1. I have to multiply by that block. And that's how I can move it here. So that's got a minus. I moved it here, I moved it here, I moved it here, and this also is going to have a minus to it. So I can rewrite my block diagram a different way. Vn comes in. I've got a Km over Rm, R2 over R1. That's one block. You know, I'm going to go ahead and put this D on here for now, and then I'm just going to ignore it. So I'm going to say the D is equal to 0. I'm going to choose to do this one a different way. 1 over J equivalent S plus B equivalent. These are both the same thing. And this is omega out. And now I'm going to put over here, this is R2 over R1. I've got a KE, KM, another R2 over R1. And then it's going to come up here, and here's a minus sign. Okay? So I've taken my block diagram. It's a little bit different form than we saw in the last one. I've changed it into this way. And then I see that there is a loop. Aha! A loop. I want to mess with the loop. And if I mess with the loop, so for now I'm just going to ignore D. Neglect. I'll get back to that in a moment. Here's a loop. And if I go and I'm going to work with that loop here. It's the feed forward. Okay, remember what the formula is. Feed forward over 1 plus the feed forward times the feed back. Okay, so it's the feed forward. It is 1 over J equivalent S plus B equivalent divided by 1 plus the feed forward times the feed back. So that's 1 over J equivalent S plus B equivalent times the feedback, which is R2 over R1 squared KE KM. And then, as always, I'm going to clear the fraction here. I'm going to clear the fraction by saying J equivalent S plus B equivalent. J equivalent S plus B equivalent. Okay, so now we've got that. I'm going to set that is going to be equal to, well, those two cancel out. This is 1 over J equivalent S, 1 over J equivalent S plus B equivalent plus KE, KM, R2 over R1 squared over RM. Because see here, I had the RM here, and I forgot the RM here. So that's got an RM in it, so it has to get multiplied by RM, Km over R2 over R1, and there's already a KE, R2 over R1 there. Okay? So look here. These two things, they don't have any S on them. This has an S, so it has to stay that way. And these two things don't have any S on them. And so what I'm going to do, this is B equivalent prime, by the way. Better make sure I've got that here. That's B equivalent prime. And so what I could say is that B equivalent is the total damping. And now I can say what B equivalent is. B equivalent is going to be whatever the output damping is, whatever the motor damping is, times R2 over R1 squared, plus R2 over R1 squared, KE, Km, it's the motor torque constant, the back EMF constant over the motor resistance. So J equivalent is equal to the output plus the inertia of the motor times R 2 over R1 squared. Output over the input. Okay. So I can kind of look at two transfer functions that I can have. I can have, say, let's go T sub V. I'm going to look at how to make T sub V, and it's going to look like this. T sub V is going to be the output, omega out, over the input, V in. And what it's going to look like is Km over Rm, R2 over R1, divided by J equivalent S plus, plus B equivalent. So that's the part that is only due to the input V in, because I just neglected D. And there's another block diagram that I can draw here, and that says, oh, you know what? Suppose that I neglect the voltage. Well, then the way that moves is if I have a disturbance in here. This is disturbance is plus, and this is going to be 1 over J equivalent S plus B equivalent. And here's omega out. So there's another one. I'm going to call this T sub D, and it looks like this. Omega out. How does omega out change with D? And that is 1 over J equivalent S plus B equivalent. Those are two different transfer functions. One transfer function, if you can do one of them, you set D equals 0, change the voltage. You can do the other one, set the voltage equal to 0, change the disturbance. Those are two different ways of doing it. All right.